Okay, so in the previous lecture, we were looking at the file systems, right, used by the Unix-based operating systems. So we have, the introductory file system, which was introduced long time ago. But then there were extended file systems, which are called ext2, ext3, ext4, and with minor changes. As I mentioned in the ext2, the main change was that instead of having a single or unified file structure, we had groups, right? Block groups. So the disk was divided into the physical division, which is what we call partitions, and then in each of those partitions, then you have this particular structure, right? Similarly, you have ext3. The only difference between the ext2 and ext3 is that there was an addition of this general area, which is nothing but a cache area in the disk, right? So initially, the file content can be written over here, and then in the background process, it will take the file content from there and then appropriately write it into a particular data block. And then ext4 is the only difference is the amount of the size of the disk and the file sizes that it supports, which are much larger compared to ext3, and also directory entries. So this is the basic idea or basic structure of the file system that is stored in the disk. Now, I mentioned here a couple of times about inode, right? So we have something called as inode. Now, what is an inode? So what happens is that every operating system has to store a metadata about the files and directories in in some data structure, in some structure, right? So for example, Windows uses a file system called NTFS. Okay, Unix-based operating system uses a file system called ext, right? So each of these file systems has a particular structure, a data structure in which it stores the metadata information about the files and directories. So in case of Unix-based file system or UFS, that is called inode. So inode is the name given to the name given to that structure, which we also commonly called as FCB or file control block. So even in the Windows operating system or any other operating system that you may be using, there is something called as file control block, which is a generic name, but specific to the Unix environment, that file control block is called inode. Okay, and what does inode contain? So inode contains the information about the permissions to the directory or files, the file size, the times, right? It keeps track of the times for the creation, access, and modification, and then it keeps track of the addresses or the addresses of the data blocks, right? Meaning where the actual data of this particular file is located in the data block. So if you recall, I mentioned earlier that you have a data block here, and in the inode table, so this is the entry we are looking at, right? The inode. So inode information is stored here, and in this inode table, it keeps track of which of these data blocks are allocated to a given file or a directory, where the actual data of that file is stored, right? So how do we keep track of that? So in order to do that, what the inode structure does, it stores the addresses of the data blocks. Okay, so let's assume that there are 10 locations over here in inode, which stores the direct address of the block in the data block area, which contains the actual data, right? Which contains the actual data. So this is what we call direct, direct block, right? So direct block means that it is the block where you store the address, and that address is pointing to the block of data in the data block area, which contains the actual data. Now these blocks can be 2K, 4K, depending on the setting that you would have done in the operating system. So operating system basically decides that how to divide the disk into number of blocks and what would be the size of the block. Okay, so let's assume that each of these blocks were 2K blocks, right? Assume that these blocks were 2K blocks. Now, if you had a 2K block, that means if you are able to store 10 addresses here, that means maximum size of this particular file can be only 20K, right? Because you are storing 10 addresses, 2K block for each addresses. If you had 8K block, then you will be able to store maximum of 80 kilobyte of data in your file. But we know that we need to support the file size of this size, 16 terabyte, 2 terabyte, right? So these are the file sizes we need to support. So that means you need to actually store that many addresses in your inode structure. But directly storing that many addresses over here will actually be a problem, because then your inode itself will require more space than 8K or 2K. And because you will have to store that many addresses, and that is a problem. So how do we solve that problem? We solve that problem by doing the indirect block. And what is an indirect block? So indirect block basically says that indirection means that instead of storing the address of directly the data block, you are storing the address of a block which may also be part of the data block only, meaning that maybe there is a block here somewhere in the data block, but that block does not actually store the real file data. That block also is storing the addresses of the other blocks. That is why the name indirect. So this is a direct addressing. Direct addressing means that this is an address of a direct data block. Whereas here it is an indirect block, because this is an address of a data block, but then data block, meaning the block in the data area. But this particular block does not actually contain the actual data. Okay, so let's assume that this is also one of these blocks, the same size of that block which is used here. And if you were to use here 2K size, right? So this block is, let's say, 2K, and each of your addresses are, let's say, for example, 32-bit. Okay, so each of your addresses are 32-bit, and if you had 2K block, 2K size of this block, then you can store 64 such addresses. Okay? So you have 64 addresses here, and each of those addresses will be then pointing to the actual data block. So by using one of the block from the data area to actually store the address instead of storing the data block, you are able to point to many other data blocks. So now, if I just use this one indirect block, then you have 64 multiplied by 2K. Right? 64 multiplied by 2K. So I can actually store the file size of 128K here, plus 20K here. So 20K plus 128K. So I can actually have the file size maximum of 148K. Okay. I need more space to store the file also, because I need terabytes, right? So I need to go megabyte, gigabyte, terabyte. So what people have done is they have done double and triple indirection. Okay? So double and triple indirection works similar to this one. The only difference is that now here it is the address of another block. This block will store 64 addresses. Again, each of these addresses are again not the actual address of the data block, but these are the addresses of another block, and that block also is storing the addresses only. So this is what we call double indirection, right? So you have the address for the block, then again you have the address for the block, and then you have the address for the data block. So this is what we call double indirection. And in this case, now if you look at the size of the data that you can accommodate here will be 2K multiplied by 64 multiplied by 64. right? So 64 times 64 times 2K. That will be the size that this one particular indirect block will be able to take care of. Plus 64 times 2K and plus 10 times 2K. So that will be the total file size that you can accommodate if you have a single double indirect block, single indirect block, and then 10 direct block. Okay, you can go further down, right? I mean, you can have as many levels as you want here. So let's say you can use triple indirect block. In that case, you have the address block, then again you have the address block, again you have the address block, then you have the data block. So here now you are able to store 2K multiply by 64, multiply by 64, multiply by 64, and so on. Okay, so what I'm trying to say is that using this inode structure, you can determine what will be the size of the file that you will be able to accommodate. Okay, and this is how the addresses of the data blocks are stored in the inode. So if you want to look at sort of like what are the different fields that the inode structure has, I put that slide also in text format. So you have the file owner, right? So we obviously, when you do ls command, we get an information about who is the file owner, right? So for example, this is the user ID who owns this file or directory, right? This is also the group ID who owns the directory or a file. So you can get the information about the group owner and the file owner. You can get the information about the type of the file. So where that information is there, it is the first character here, right? So hyphen means it is a regular file. D means it is a directory. L means it will be a link, and you don't know what is link right now. I'll come to that in next couple of slides. So you get information about such things. You also get information about whether the entry that you have in the inode, is it a character device or a block device. So what happens is that every device that you are using on a computer, whether it is a keyboard, mouse, screen, USB drive, network port, anything, right? Anything at all, HDMI port, RGB port, whatever ports that you are using, right? All of those devices are also considered as a special file as far as the Unix-based operating system is concerned. Okay, and there will be a directory entry for each of those devices as well. And that is what is also included in the file type. Okay, and if you go to the dev directory, that information is there. So dev directory is the directory where the devices that you have on your system are actually listed out. Okay, and I'll come to that when we look at the directory structure of the Unix-based operating system. But you can see that this one, C, stands for character device. Okay, so your keyboard, mouse, screen, those are all character devices. Then there will be some with B, right? B are for block devices. Okay, so block device is something like USB drive. Okay, so wherever the data can be transferred in blocks, meaning that more than one character, more than one byte at a time, then those devices are called block devices. If you can only transfer a single byte at a time, then those devices are called character devices. Okay, so those kind of information also you can get from here. Okay, you get an information about the access permission. We know that, right? So when you look at these permissions, these are the access permissions, right? So first 3 characters are for the user, then the next 3 characters are for the group, and then the last 3 characters are for the other users which are not in the group. So that information also you have. You have the times which are stored for the creation, last access, and last modification. Okay. You have the information about number of links, which I said I'll come to that in next 2-3 slides, or maybe 5 slides. Size of the file, if it is a regular file or a directory, It will also be able to store the major and minor numbers which are usually used for the devices. So if you look at, since this is a dev directory, if you look at these numbers represent major and minor numbers for a device. And in case if we happen to have a time in the towards the end of the course, and if I'm able to cover a little bit about device drivers, I'll cover what these numbers are. Or if you are interested to know about this one, we can get offline as well. Right? So this is the information about the device. If you go to any other directory, then you will see the sizes of the file. So for example, this is telling me that 3096 is the size of this file, right? 98 bytes is the size of this file. Each of the directory by default contains 4K size, right? So this is what the information you can get from the inode. Plus, you can see the data location. So these are the addresses for the for the data blocks, right? So this is the information you get from your inode. Okay. Now, inode is not just the name, right? It is also a number assigned by the operating system. So whenever the file is created, or directory is created, or device is created, or links are created, it assigns a specific number, and that number can also be accessed using the ls command. But for that, we have to use a switch called -i. So -i switch. So again, if you look at the man page for ls command, and if you look for -i switch, right, it tells you that it will print the index number or inode number for each file or directory. Okay, so -i is the switch used to get the information about the inode number. So let me do -i here, and you see that there is a number printed in front of each directory and each file. Okay, this number is nothing but an inode number. Okay, so what is this inode number? Inode number is nothing but the number that is assigned to a particular directory entry or a particular FCB for that file or that directory, right? So we said that every file and directory has this FCB structure, and this FCB structure is what is stored in this inode table. So this inode table basically contains this FCB structure. Okay, and for each of these structure that is stored in the inode table, right, there is a number assigned, so that we know that which file name or which directory or which device or which link has what number assigned, which inode number assigned. And that number is what we are reading using that -i switch. Okay, couple more information that you should know about the inode is that we have the directories, right, in a particular structure. So we have a hierarchy of the directory. So when you look at the hierarchy, how do we look at the hierarchy? So let me go to the root directory. So cd// is my root directory, and if I look at ls-i, right, you will see that there are subdirectories in my root directories, and each of these subdirectories have been assigned an inode number. So for example, when I look at my home directory, right, home directory has inode number 222.8225. Right? Now, if I go cd home, which means I'm now going to the home folder, right, a child folder, home, right? And now I can do ls-i, and I can do a. So there are certain hidden directories inside each of the directories, and those hidden, at least there are two hidden directories. One is called dot, which stands for the current directory, and another is double dot, which stands for the parent directory. Because if you recall, we always run a command like this, cd space ... to go to the parent directory, right? And it is able to take us to the parent directory. How it is able to do that? It is able to do that because it is able to find out what is the inode number of the parent directory of this current directory. So what will happen is, if you look at ls minus ia, a is the switch to look for directory entries even if they are hidden. Right? When I do ls minus ia, you will see that there are two additional entries that you will see over here. Okay, so for the root directory, we see these two additional entries, which is dot and double dot. Okay, so dot indicates that it is the current directory address, and double dot indicates it is the parent directory's address. But the point is, you are in the root directory, and root directory does not have a parent. Right? That is why it is a root, right? It's basically mother of all directories. That is the first directory that you land at, right? So the root directory, which is a / directory, does not have any parent. And therefore, if you look at the inode number, so the inode number for the current directory, which is the root directory, is number 2. Similarly, the inode number for the parent directory is also 2. So basically what operating system is telling us is that because root directory does not have any parent directory, the inode number for the parent directory as well as the current directory is same. And this will be the only directory in whole of the drive will have this scenario, right? So this scenario only occurs for a root directory. Okay, and if you don't believe me, I'll show you why, right? So now let me go to the home directory. Okay, so what we will also notice is what is the inode number for home directory. Inode number for the home directory is 2228225, right? Now I go to home directory, and now I do ls minus ia. Now if you look at ls minus ia, you again see these two directories, right? Single dot and double dot. So single dot stands for the current directory, right? As I mentioned. So which means it is a home directory we are talking about, right? So the inode number for the home directory is this one, 2228225, and you see that the same thing is being displayed here. So operating system knows that the child directory home in my root folder has the inode number this, and the same inode number is also mentioned as the current directory in the home folder itself. That is what this is. And then when I look at the parent directory for home, right? So double dot means it's a parent directory. So when I look at the parent directory for home, the inode number there is 2. So it knows that the parent directory of home is 2, which is my root. Okay, I go one level down further, right? So under home directory, I will be able to see the subdirectory with my user ID, which is my home folder, right? So I'm going to say this one. And now I will look at ls minus ia again here, okay? And you will see that the inode number displayed for this particular folder, this particular subdirectory in my home folder is this 2228226, and the same thing is being mentioned in the current directory's inode number under this user, under this particular folder. And the parent directory inode number in this Ubuntu 20HP is 2228225, which is the same as the current directory's number or the home directory's number, inode number, right? So this is basically the chain. It's basically creating the hierarchy using the inode number. So inode numbers are very, very important for you to understand, because that actually defines the directory structure in the Ubuntu-based operating system or Unix-based operating systems. Clear to everyone, hopefully? so when you look at this hierarchy, is what is defined by the inode number is what I was going to say, right? So inode numbers are the ones which are basically telling you that which are the files under these directories, and then if there are subdirectories, then they also have the inode numbers, and the subdirectories then have another files or other subdirectories which also has the inode number, and the parent directory will have information about the child directories and files inode numbers. Similarly, your child directory will have the information about the parent's inode number also. So both information is available to you, right? So therefore, when you go to the child, when you change your directory to child, you are able to do it. Again, when you say that you want to go to the parent directory, you are also able to do that, because both inode has an information about the child and the parent. Clear to everyone? Now this is the slide that I was talking about earlier, which shows that what is the directory structure that generally when you install a Linux-based operating system, what is the hierarchy that you have, right? So as I said, you have a root directory, and which is represented by a forward slash. Right? Forward slash is basically your root directory, and that is the mother of all directories, right? That is the first directory that's been created in the file system. Okay. Then you have the build directories. So whatever utilities, whatever the shell commands we are using, right? So we are using remove, we are using move, we are using cat, we are using gedit, we are using cd and all those commands, pwd, all of those commands that we are using, all the binary files of those programs, those applications are located in the bin directory. Then there's a boot folder. This is the folder where the booting, when you start your operating system, it requires certain files also, right, for booting up. Those files are available in this boot folder. Okay, so boot folder is where the bootloader is. Bootloader is basically the files that are required to start your system. Okay, and I'll talk about the booting process, I believe, later in the next chapter, where I will show you the content of the couple of files so that you understand how the booting really works. There's an etc folder which contains the configuration files for the system. So let's say configuration about networking, configuration about shell, configuration about the host information, right? All of that information is actually stored here. If you recall, when we wanted to tell operating system to look for a library, dynamic library in a particular folder, we had to go to etc/ld/soconf, right? So that was the folder we went to, right? So that is also configuration file, and it is in the etc folder. Okay. OPT is the folder where you have again some additional configuration files for application specific. So the OPT stands for optional, right? So there are some optional configuration files that may be required for certain applications. So that is stored over here. Then there's a user folder. Under user folder, you have the local, you have the share, bin, include, lib, and so on, right? So you have the local binaries will be stored here. These binaries will be here, right, in bin folder. Header files will be here, lib files will be here, but these files are specific to that particular user. Okay, it is not applicable to all the users. So let's say if you log into that particular system, you will see different set of files over here than a different user logging into that system, because this directory has a user specific data. Okay, some variables information also needs to be stored in file, right? So there are some global variables which operating system uses. For example, one of the things that we may see will be for the locking mechanism that we will study in the threading component, right? So some of those files are actually located over here, right? Or some of the logs that you are creating as part of system booting and all that, those logs are also located here. There's a temp directory, there's a dev directory. Dev directory I talked about. All the devices that you have in the system, the files for those devices are actually located here, right? Home directory is there, lib directory is there, and so on. So in short, this is sort of like the directory structure that you would generally see whenever you look at the Unix-based operating system. Okay. Now we come to the links type of so when you look at the again Unix-based OS, the files, directories, and links, these are the three major kind of entries that you will see in your general directory. Okay. So what are links in the first, right? I mean, what is a link? What in this slide, basically what I'm trying to show is that you have the inode list here, inode table. Okay, and you have the inode table where the inode information is stored for a different file, right? So assume that there are multiple inode information that is stored here, which is the inode table, and this inode, each of these inodes are pointing to different data blocks for the files. Okay, now when you look at the link, there are two types of links available. One is called hard link, the other one is called soft link or a symbolic link. So symbolic link slash soft link means the same thing. What is the difference between the two? So what happens is, as I have mentioned, that each of the file or a directory entry or directory, right, that you create has a inode number assigned. And that inode number is basically your FCB structure. So what happens is that whenever you create a new file or directory, it creates what is called as hard link entry into the directory. So that particular directory where you create a file, right, or create a directory, it creates a directory entry, and that directory entry is what we call hard link. Okay, so hard link basically has an information about the inode number and the file name, which is where your FCB structure is stored, or inode structure is stored. So this is the entry, this is the table entry, right, which is where the inode structure is stored, and this is the name. The file name is the name given to that inode number, is what we are saying when we say hard link. Okay, now you could create multiple hard link for the same inode, same FCB structure. Okay, so I can say that file name 1 with the same inode number, file name 2 with the same inode number. So in short, I'm giving two different file names, but it has the same inode number. Okay, so which means that you can actually create multiple links for for the same for the same inode. Okay, sometimes we do that because we are in a different directory and you want to actually create a link to that file by not going to too many other directories and something like that, right? So basic idea behind creating the hard link is you have multiple names to the same inode structure.
So sir, it's like creating shortcut on desktop.
It's like creating shortcut on desktop, right? Yeah. So link itself means shortcut. Okay, but we have two types of shortcut here. One is hard link, the other one is a soft link. Soft link is also a shortcut. But what this soft link does, soft link is actually a new entry which is not directly pointing to the inode structure, but it is pointing to the hard links directory entry. Okay, and by theoretical understanding, if it is not clear to you, better way to see it is by exercise, right? So we want to actually see how it really works. So what we will do is first we will create a hard link, and in order to create the hard link, you need to use ln command. ln is the shell command which creates the links. You can use the hard link using the same command. You can use the soft link using the same command. If you provide -s switch, lowercase s, which says create a symbolic link. Symbolic link is soft link instead of hard link. So what I'll do is I'll use our file. I'll use our file, the shell file, and create a hard link using that. So ln mount that file name, and then I'm going to call this as mount hard. So now if I say ls -ia mount star, so you see that there are two mount files, mount star files, right? One is my original shell file, and this is the new one that I have created, which is again my hard link. Okay, but interesting thing is this number over here. What is this number? This number represents the inode value, inode number, right? Index number in my inode table. And that index number is exactly the same. What does it mean? It means I have two files, two names with the same inode number, meaning that both are pointing to the same inode. Okay, this is what the hard link means. So what happens if I remove one of these hard link? The other hard link still works, because this is pointing to the same inode, and inode has the same data blocks list. So let's say, for example, if I remove my original file, right? If I remove this file,
Sir.
yes.
So, in hard link, the exact copy of original file is created?
No, that is exactly what I'm trying to tell you. It is not the copy. It is not the copy. Both there is two separate directory entries are created, but both the directory entries are pointing to the same inode table entry. So it is not copy of the file. It is the same file, but the same file is being referenced from two different directory entries, and two different directory entries have been given two different names. That's all. Understood?
Yes.
Okay. So even if I remove that original original file name, you will be able to see that I can still run this shell script using my new hard link. Okay, my new hard link works and runs my shell script even if I have deleted my original file name, because this original file name was nothing but a hard link. And because in case of hard link, both the hard links are pointing to the same FCB, same inode entry, right? It is basically I'm pointing to the same file twice using two different names. That's all, right? Because it basically had the same inode number. So if you also if you modify, if you basically change permission and something like that on one of them, the other one will not be affected by it, right? So what we can do is we can actually play with these hard links for multiple users. So multiple users may require different different types of access and things like that. You can actually play around with the hard links. Now, soft link doesn't work the same way. Okay, so what happens in case of soft link is that soft link, as I said, it's an indirect addressing kind of thing. So what is an indirect addressing? Meaning that it will create a new directory entry, yes, but it will not point to the same inode number. It will point to, it will be basically creating a new FCB, new inode, and that inode, that new inode, is then going to say that I'm now going to point to the original inode. And maybe, you know, instead of talking about it, let me just create. Okay, let me answer your question first with the copy of the file, right? So what will happen is, let's say instead of creating a hard link, right? So how do I create a hard link? I can say ln mount hard, and then I can say mount host files.sh. And if I do this, again, my mount hard and host file.sh has the same inode number. What you are talking about is copy of a file, right? How do you create a copy of a file? I can say cp command. So I can say cp mount hard, and then I'll call mount hard1. So I'm basically creating the copy of this file into this one, right? Into this one. And now if I look at the inode numbers, you will notice that the inode numbers are not same, right? So now the file content is the same, but the inode number is different. So when you say copy of the file, this is what happens when you copy the file. Okay, but when you create a link, you are not creating a copy of the file. It is pointing to the same inode entry, same FCB structure. That is what we are talking about. Okay.
Sir,
Now let me create. Yes.
Sir, what the number in first column represented?
That's the
number
inode number. That's the inode number. That is what I'm saying. So for
first
this
column.
particular file, no, this is three different columns, right? So these are the files, and for that, this is the inode number. These are the files. This is the inode number. These are the files. This is the inode number. So this directory has many files, so it is listed like this.
Okay.
So
Hello,
now,
sir.
yes.
Sir, can you please turn off your video because the presentation is lagging and audio is very choppy. So,
Okay. Better?
yes, sir.
Okay. All right. So now I am going to create a soft link, right? So I'll say ln minus s, and then I'm going to say mount soft, and then I'll say mount host files. Okay. Or actually, I should do mount host files, and then I should do mount soft, because first I have to give the original file name, and then it is the link name. Okay. Now if I do lia, okay, and I should actually do lia. I need to see the long format. So you will notice that this is my soft link which I've created. Okay. What is the inode number? This is the inode number. This is my original hard link on which I've created the soft link. So you will compare this inode number and this inode number, and they are different. Whereas this inode number and this inode number is the same because they are the hard links to the same inode. Okay. So what basically here it is doing is it is creating a new directory entry and pointing to another hard link. So it is not creating a new hard link which is pointing to the same inode structure, but it has created a completely new inode structure, and that completely new inode structure is pointing to the old inode structure. That is what soft link is doing. So what will happen is, in case if I change something in this file, or if I make this file unavailable, so let me rename that file. Instead of deleting, I'm just going to rename that file. And now if I do LIA, and you will notice that this soft link has turned into red color. Why did it turn into red color? Is because the soft link is not accessible now. Soft link is not valid now, because the hard link, which was being pointed by this soft link has no, it is no longer available, right? We have changed the name of that hard link, and therefore the soft link is invalid now, right? And why do I know this is a soft link? Because you can see there is a L over here. So L indicates the soft link, this indicates the regular file, this indicates the directory. So if I try to run my soft link command, it will tell me that no such file or directory. But if I move back if I rename my original file back to the original name, I'll be able to run my soft link, because my soft link is now recovered again, right? It's recovered again. So this is the major difference between the soft link and the hard link. Okay. So if you look at this slide, it says that the hard link, when you make a change to the original file, it will not affect another hard link which you have created, right? Because original file is also a hard link actually, right? And then you create a separate hard link, and if you make a change, or if you delete the original file name or original hard link, the new hard link will still point to the same inode and will continue to function. The disadvantage of the hard link is that it cannot span across the file systems. Okay, and what that means, I'll just come to that. In case of soft link, if you make a change to the original file, it will affect the soft link, because again it's an indirect pointing, right? So your soft link is a new inode entry, and that soft link is pointing to one of the hard links. And if you make it, if you make that hard link inaccessible, then your soft link will become inactive or invalid, right? But then the advantage of the soft link is it can span across the file system. What does that mean? Let me show you. So we know that we have mounted our host files folder, and that host file folder is actually a folder located in my Windows file system. And Windows file system is a different file system than the ext file system. So it is an NTFS file system, right? So if I try to create a link, right? If I try to create a link into my NTFS file system, okay? Let's say I want to create a hard link called file.io, and that is supposed to be pointing to this particular folder, which is sitting on my Windows system. It tells me hard link not allowed for the directory, because this directory is not actually the real directory in my Unix operating system, in my Ubuntu. This directory structure is actually in Windows, right? It's an NTFS, NTFS structure. So I'm not allowed to point using hard link to that one. But if I use a soft link, right? If I use a soft link, I can do that. So you will see that file.io is the soft link or the name given to this particular folder. And if I just do cd file.io, I can then basically directly go to that directory where the file.io files are there, right? So this is the basic difference between the soft link and the hard link. Clear to everyone? Okay. Now coming to inode information, as I said that inode actually stores a lot of information, right? And we can see that in the directory information when you do ls using inode information. You can use long format to get the owner and the group information and so on. But if you want to get that information inside in your program, in your C program, how would you do that? Right? So just looking at the information is not enough. Sometimes we need to use that information inside our code. For example, if you want to know whether a particular file has a read permission or not for a given user before you try to read the file, okay? Or if you want to know what is the size of the file. So if you want to get that kind of information, you have to read that inode structure. And to do that, operating system has provided a structure called stat. So stat or stat structure has the information about the inode. Whatever fields that are available, important fields that are available in the inode, the same fields that they have provided here in this structure. So mode provides the information about the file type and the permissions. Then you have the inode number, you have the device number, you have the number of links. Number of links are basically to count number of hard links. Okay. User, who is the owner of the file or directory, group, who is the owner of the file or directory, size of the file, access time, last modification time, the creation time, block size, right? IO block size. So this is what I was talking about, data block size, right? What is the size of the block and the number of disk blocks that is allocated. So by looking at this also, you can kind of figure out what would be the setting that operating system has. Right? So all of this information you can actually retrieve. And the operating system has provided us 3 system calls. We call this system calls because they are the functions provided by operating system. So normally, you call it as a system function or a user defined function. System functions, we also sometimes call it as system calls because they are the system functions developed inside the operating system. Okay, so stat is again the name given to the system function. You can provide the complete file name with path, and it will return you the pointer to the stat structure. Okay, return you the pointer to the stat structure, which will then provide all of this information. The forward declaration and the stat structure is defined in these 2 header files, okay, which is what you need to include in your program. If you already have open file, right, if you have already opened this file and you already have the file handle or file descriptor, right, the number which operating system will assign when every single file is opened, right, then using that file descriptor, you can also read the stat structure. If there's a link information, you want to get some additional data there, you can use lstat for soft links. Okay. So what we will do is we'll look at a couple of examples here so that we know what information we can read. So for example, if you want to read the inode number and number of links as an example, right? We will look at that code. So what this code does, simply accepts the argument, which could be a file or a directory, and then it is reading the mode information. So mode information I'm just displaying here. We are not doing anything right now in the mode field. We will do that in the next example. But here we are displaying the inode number and the number of hard links, right? So inode number and number of hard links. That is what we are doing. So this program is already compiled, so I'm just going to go to that directory, which is where I am currently, and I'm going to just run stat links.out. Okay, and I'm going to provide. So let me just do ls home. Okay. Now, if you see here, we can use mount hard or mount host files, and they both are pointing to the same inode. So either one, if I use, I should get the number of links as 2, right? And I should get the same inode number. If I use mount hard 1, or mount soft, I should get the link as 1, and I should get that respective, inode number, right? So that is what I'm going to do, right? So let me do stat links dot out, and we will then provide mount host files dot sh, right? And if you see that it says that this is the mode value, which I'll come to later, this is the inode number. So I'm able to read that inode number in my C program, and I'm also able to get the information about the number of hard links. Okay, so for this particular inode, there are 2 hard links, and instead of providing this name, if I provide hard, I will again get the same information, because both of them are hard links to the same inode, right? Both of these are hard links to the same inode. Instead of that, if I provide soft, then the soft also gives me 2, because the soft is pointing to this particular hard link, and this hard link inode has 2 links, right? That's why. Let me do hard 1. When I do hard 1, it only gives me link as 1, because that particular inode, right, this particular inode, this is the hard link, and that hard link only has a single, that inode only has a single hard link to it. So therefore, so you can get, these information using that stat structure. Now what we are going to do is we are going to get an information about the access, right, the permissions, because many times, like I said, in your C program, you want to check that what is the permission given to a file. And first of all, you want to check whether it is a file, whether it's a directory. If it's a directory, maybe you want to do something else. If it's a regular file, you want to do something else, and so on, right? So there are bits. So this mode is the type of mode T, and if you look at what is the what is this user defined data type in the types.h, you would notice that it's a 32-bit number, right? 32-bit number, and that's why we are getting this 4 hexadecimal values here, right? 4 hexadecimal value. So so each of these bits, right? So each of these bytes will have several bits, and each of those bits represents something, right? Represents something. Now, instead of us remembering which bit is doing what operating system has done is they have provided us a direct constant value. Okay, so these are all hash defines, and this hash define has the bit pattern which represents a regular file. Okay, so a bit pattern which represents a regular file is what is defined by this constant. Okay, this constant is defining the bit pattern which represents the directory in the mode field, in this particular field, right, and so on, right? They've also given macros. So if you don't directly want to use these bit patterns, you can actually directly use these macros that will check for this bit pattern, and it will return true or false, whether it is a regular file or whether it is a directory or whether it is a link. Okay, but then for the checking of the permission, you still have to work on the bit patterns. Okay, so if you want to check for a read permission for a owner, for a user, the current user who is logged in, not owner, the current user who has logged in, right, to the system and who is running this program, for that particular user, if you want to check for a read permission, you use this particular constant which has a specific bit pattern set. Okay, this is for the write permission and execute permission for the current user. If you want to check for all the 3 permissions, then you can use this particular constant, and this are only for the current user who is logged in. If you want to check for the groups, you will provide either GRP in these 3 cases, GRP instead of USR, right? And here, instead of U, you will provide G. For the other users, who are not in the group, same as the current user. For the other users, you will be checking for OTH here, and you will be replacing this U with O. Okay, so this is how you will be able to check whether you have a read, write, or execute permission to a given file or a directory. Okay, so what we will do is we will run that example and see that how it really works. So in that example, what we have done is again accepted an argument for a file or directory or a link, whatever you provide. Then we have used the stat and lstat to read the the stat structure, right, information, and then just displaying the mode value here, right, just so that we know what is the mode value. And then I'm checking here, right, whether it is a link. So for the link, we have to check into LST mode for this particular macro. Okay, but for the regular file and directory, we have to check in this stat structure. So in this stat structure, we can look at a particular bit pattern by using this macro and see whether it is a regular file or a directory. But if it is not a regular file or directory, we have to look at the lstat or rather stat structure, but with the different macro, right, for the link, right? And then once you have that information, then you can display the file type, and then these blocks are to check a bit pattern. So you can see that I've done the ending, and this ending is your bit ending, right? This is not your logical end. This is your bitwise operation, right? So we are basically saying that whatever is your ST mode value, do the bitwise ending with the reading of the user bit pattern, right? So with this pattern, it will do the ending, and it will check whether the answer or the condition returns me true or false, right? If this value is 0, that means it doesn't have a read permission. If this value returns 1, then it does have the read permission, and so on, right? So it will check for read, write, execute, and all three here. Similarly, we are also checking for the group permissions. Okay, so using this code, you can then check whether you have the sufficient permission or not. So let me run that example. Okay, so I guess first of all, let me okay. So when we look at, let's say, this file, mydir.txt, it has a read-write permission but no execute, and read-write permission but no execute for current user and a group, right? When you look at our files, our hard links or soft links, all of them has read-write and execute permissions. Okay. When you look at, let's say, a desktop folder, a desktop directory, then the current user has RWX, but then the group users does not have the write permission to that, right? So basically, since the desktop is user specific, no other user is allowed to write into that folder, is what we are saying here, right? So let us run the code and see that is the permission we are getting. Okay, so this is the decimal value for the mode member, right? And then it is telling me that this is a regular file because that is what the bit pattern says. And then it says that it does have the read permission, does have the write permission, but does not have the execute permission, right? And similarly, group users also has read and write permission, but not the execute permission. Now, if I run the same code with our file, okay, you can see that the value changes, 33204, 33277, right? And now it says that the current user has the read, write, and execute permission. Also, the group user has read, write, and execute permission, right? And now I will look at the directory, desktop directory, okay? And it says that it is a directory, not a file, and it does have read, write, execute permission for the current user, but then it only has read and execute permission for the other user. Okay. So by looking at these macros and these bit patterns, you can actually understand, or you can get the information about what kind of permissions has been given to links to directories to regular files. Questions? Okay. Now we are going to talk about the library functions or the system calls that are available to us as a shell command, right? So we use a lot of shell commands, through this terminal window, right? And all of those shell commands also has an equivalent library functions or system calls, okay? Which is what is the next two slides is going to mention, right? So access is the shortcut or a function that provides you the mode, file permission information, right? Again, you can do that using the stat, system call, but simpler version is also available over here. chown is the command that we use to change the ownership of the file, right? So you can do the same thing using the C function. Truncating the file, making the file size 0 also can be done. Creating the hard link, right, using the link system call. Removing the hard link using the ulink system call or even soft link. So, and then symlink is to create a symbolic link or a soft link. So you can see whatever ln command does, right? ln with the hard link and with the soft link, all of that can be done over here. If you want to read the information from the link, right, from the file, using the link, right? If you do read link, it will perform the open, read, and close operation altogether. You can do remove directory, right? You can do removing of the file. You can do renaming of the file or directory. You can do change mode. So change mode is to change the file permission, right? So we use change mode also on the terminal window. Same thing can be done using this system call. Creating a new directory using make dir. So what I'm trying to say is that you have all of these functions, all of these system calls that are also available in as a system call or as a library function that can be used in your C program, right? Whatever can be done in the terminal window, same thing can be done also in your C program. So we'll not implement all of these functions. Some of these functions I may have used in some examples, but I just wanted to make sure that you know that all the general commands that we have used in the terminal window, those can be also be used inside the C program. Okay. Now, generally speaking, I think whenever you have learned the file IO, right, what we have learned is how to open a file, how to read from a file, how to write into a file, how to close a file and all that. But have you ever dealt with directories? Have you ever dealt with how to read the directory entry and how to iterate through the directory entries, right? So let's say you have a directory where you have, for example, here, when we look at home folder, right, you have all these entries in the directory. How do you iterate through each one of them, and how do we get, let's say, relevant information that what we are interested in? We may not have done that. You may not have done that earlier, right? That is what we want to do now, right? So there is a dir ent header file which contains a structure with only two attributes. With only two attributes. Okay. So this attribute is the directory entries inode number. So this is nothing but this particular value. Well, I didn't do LIA. So that, this member of the structure, right? This member of the structure is nothing but this particular value. Okay, those inode values, and then you have the name. You have the name of the entry, which is nothing but this name, these names. So only these two information is available in a structure called dir, and that dir structure is defined in dir ent.h, and dir ent just stands for directory entry, right? So directory entry is the header file, which is where the dir structure is defined, and that structure has nothing but these two information. So you can get the entries inode number and the name, right? And that name could be a directory name, it could be a file name, it could be a link name, it doesn't matter. Okay, so that is the information that you can get. And you have the system calls that you can use to operate on the directory from the C program. So you have a system call called opendir. So you provide the path to the directory entry, and you can actually open the directory as a stream, right? So as a stream, you can open the directory. This will return me the dir pointer to the dir, right? And so what will happen is each time when I do the read dir, it will give me individual directory entry in my C program, right? So it will basically return me the structure pointer of dir ent structure, right? So dir ent pointer will be returned back to me. So I can read each entry and do something with it, whatever I need to do, right? I can do also rewind directory, I can do close directory, I can seek a directory. Seek directory means go to a particular position, right? So I can do all of these functions with the directory also, right? So what we will do, I'll stop here, but in the next lecture, we will go through this program, and I request each one of you to try and understand this program if possible before coming to the lecture, because this code has a recursive function, and it also uses these functions very nicely, right? So what we have done is we have actually implemented, we have seen PWD utility, right? We use PWD very often. PWD stands for present working directory, right? So we have seen this utility. What we are going to do is we are going to implement our own PWD utility, present working directory utility. Okay, so this is the code which I've already provided in Moodle. Try to take a look at it and try and understand. I'll go through this, in the next lecture briefly, but I want you to have a look at it before you come to the lecture, so that you sort of understand what the code does. Okay, so this is where I will stop. If you have any questions, we can cover that. Any questions?
So what do you mean by directory stream?
So directory stream is basically you are reading one entry at a time, right? So usually stream is referred to the data where you don't get all data at once, but you get partial data, right? It's like a water flow, right? So you have a water flow, which is what we call stream, right? So you don't get the whole water at once, but it's still coming in, right? Continuously coming in. That is what we call stream.
Okay, sir. Understood, sir.
Anything else? Okay. Thank you, everyone.
Hello, sir.
Yeah.
So, sir, I had a question regarding a soft link. Sir, so a soft link soft link refers to another file by its name, right, sir?
Another hard link, yeah. And hard link are nothing but the actual files.
So the
or the inode.
okay, so the contents of the soft link is a pointer that points to the hard link.
Correct.
Uh, okay, sir. So if we change another file,
Hmm.
if we change the name of another file to the
Hmm.
name of the name of the hard link, the soft link is pointing to, so then the soft link will point to that file, right?
No, so see, the point is this. This is the hard link we are using, right? For this particular soft link. And this soft link is pointing to this hard link, right? Now, let's say if I change the name here only, if I change the name here only, right? So let's say if I say move mount underscore hard to move mount underscore hard to. Now, if I do LIA, so this soft link is not going to, be affected by it, because what we have changed is a different hard link, right? Which is it's a different hard link. So this directory entry has the inode number and the file name, and we have changed the file name. We have not changed anything in the inode itself, right?
Yes, sir. Sir, my question was regarding that if we change another file's name to
Uh,
the to mount underscore host files dot sh in this case.
which file you want to change? Sorry, come again.
If we change the name of another file,
Huh.
another file to mount underscore host files dot sh, that is the hard link. This soft link is pointing
You
to.
can't. No, you can't have the same name for two files. Can you have same names for two files?
Uh, sir, means if we change the name of this original file to another file like you did before,
Huh?
and then change the name of another file, suppose my directory.txt, we
Okay.
change the files names to mount underscore host files sh,
Okay.
then mount underscore soft will point to the point to my directory.txt, right, sir?
Okay. Okay. I see
Right.
what you're saying. So basically, what you're saying is this: you want this mount underscore host files dot sh to something else, let's say, right? And then you want to say my dir dot txt to mount host file. This is what you are saying,
Yes, yes, sir.
right? This is what you are saying.
Yes, sir.
Okay. So the point is the soft link is not broken. Okay. But the point is that this file content is not the shell file content. So what will happen is that now this soft link is actually pointing to this one, but this file is not the same. So if this would have been a shell file, another shell file, it would actually run that another shell file. But in this particular case, because my dir was not a shell file, if I try to run it, it will not do anything because it is not really a shell file. Getting my point?
Yes, yes, sir.
So again, you have good questions. I would suggest that you guys try these things out, right? So you get a better understanding how these things work.
Yes.
Yeah. Any other doubt, question? Okay. So thanks everyone. I'll speak to you guys later, right?